So, hello. I hope I am live. So this will be my first real live, I guess. And here's a picture of me. Hello. So for this first stream, of course, if anybody drops by, I'll be happy to have a chat, but I don't know how many people will show up. So this is mostly like a test of my new setup. And because I'm currently teaching my wife some maths, I thought I'd just make a companion video for what I'm currently teaching her. So we want to get to probability. We actually started doing some probability, but she wanted to do some set theory to get a better sense of the foundation. So, well, I did that. So I'll try to kind of cover the same stuff here just to see how everything works out. Alright, so we want to talk about sets. So what is a set? A set is a collection of objects, wherever that may mean. So for instance, we can have a set A. One way to specify a set is to simply give a list form. So we use curly brackets and we can put anything within it. Could be shapes, but of course often, since this is math, we will have a set that contains numbers. For instance, like this. So A and B are sets, and the elements within the brackets, they are elements. Well, the elements, what? So for instance, how would we write this? For instance, if we want to say that the square is in this set, we write it like this. Or maybe we can write that the number 4 is in this set. We write it like this. And for instance, the number 7, it is not in the set B. So we use this the belong symbol with a dash through it, right? So we have to get used to that E/euro sign looking thing for sets. So very often we will illustrate sets by writing what is known as Venn diagrams. So if we have set A here, set B here, we kind of can show them all, show everything that's going on, and we'll talk about what the different regions of this diagram is. Also, very often, not always, but very often, we'll assume that A and B are in fact lying within a set, often called U, because it's a universal set. You can think it of a universe if you like. So this is kind of everything we want to consider. And and what you can see here already is that what we're kind of tacitly assuming here is that A is a subset of the universal set. And we write this with this symbol. Right. So this reaches A is a subset of U. Right. Which of course, what this means in more mathematical terms, you can say that if little a is an element in big A, the set, that will imply that A is also an element in the bigger set U. Right. And if you look at the inclusion sign like this, you can see there is this horizontal line on the bottom is the same as if you were writing less than. It means that there can also be equality. Right? So A could possibly be the entire universal set U. Right, and let's see if I can do this. That didn't work. I'm still getting used to this. Let's erase this. Of course, we also have that B is a subset of U in this case. Okay. So let us do an example. Right. So, for instance, let's say that in this example, our set A is the numbers from 1 to 4. B is the set 2, 4, and 6. And of course, as you probably have started with the universal set, but we're saying the universal set in this case is just 1 all the way up to 7. Oops. Like this. So how could we, let's see, can I make this a little smaller? Oh my god. I'm still learning the ropes here, so that's amazing. So how can we draw this? So we have the universal set. It's the big set. We have A and B. And then we need to place the elements here, right? So what we'll find out as we go here is that as there's different regions in here, that will become interesting. So for instance, you can see that 1 will be, it's in A, so it has to be within the circle, but it's not in B, so it would go here. 2, it's both in A and B, so that would have to go here in the intersection. We'll get back to this later. 3 is over here as well. It's in A, but not in B. 4 is both A and B, so it goes here. 5, as you can see, it's in neither A and B, but it is in the universal set. Then we have 6, which is in B, but not in A. Goes here. And finally you have 7, which is also in neither A and B, but also out in the universal set. Right. So you can see we naturally have divided U into some, well, areas you might say, or some subsets. So let's look at a few of them. So the first, just a minute. Let me just add the U over here. That sucked. That totally sucked. Is this the undo? That was certainly not the undo. Okay, let me just redraw it for now. But I have a feeling I would like to get a copy of this so we can draw on it. So where is the copy? I think it's here. I think it's there. Okay. I'm learning a lot of stuff here. Oh, this is page selection. I don't want that. Oops, that's not what I want at all. Right. Oh. Okay. So if I want to add page. And I want to. Wow, this is interesting. There I am. But I guess I still have this over here. It's done. No. Okay, I'll leave it for a while. Okay, once I figure this out, we'll see. So anyway, you know what? Let me just redraw everything. what is the easiest way to do this? So did I copy it? Oh, so this is like, okay. I guess, okay. Okay, at any rate, what I want to discuss is the first thing here is the union. This is the wrong one. Union of sets A and B. So if we have A and B, then the union is simply everything inside A or B. So in our case, we can see here it's 1, 2, 3, 4, and 6. 5 and 7 is not inside the set here, inside the union, because 5 and 7 are in neither of them. So that would be our example. One, 2, 3, 4, and 6. And the way to remember this U sign is because it's U for union. So that's how I remember that. We can also, a way that's very convenient to express this for more formal situations like proofs and stuff. What we can do is we can use what's called set builder notation. Set builder notation, or sometimes set comprehension, which is the fancy way of saying stuff. But the idea is that we can write the union of A and B. So the set builder, it starts with the curly brackets, just like you would any listing of elements in a set. But what we are looking for is elements in the big set that satisfies some kind of property. And this X, the naming here is totally arbitrary. You can kind of think of it as a dummy variable, if that is a terminology you're familiar with. Anyway, what must X satisfy? Well, since the union, it should either be in A or it should be in B. And here I'm using the word or, and this is what is known as an inclusive or. So for instance, in natural language, in everyday speech, if you ask somebody, do you want tea or coffee? You don't expect the answer yes, because you expect them to choose one or the other. But here, it's an inclusive or. So it's possible that both X is a member of A and X is a member of B. So you can get both tea and coffee in this situation. All right. So, or this is in. Oops, that was wrong. I'm so used to writing Danish. Inclusive or. Right. So both can be true. And because mathematicians are allergic to ordinary words, sometimes, of course, we have a symbol instead of this inclusive or. And let me just rewrite it. Alright, so we have the X in the universal set, which satisfies, I don't know if I forgot that, but you have like the vertical line. That's kind of separating the set from which we we're taking elements from and the condition to be satisfied. But anyway, we can have, so either X is in A or X is in B. So this symbol here, that means or. And you can see that it's kind of similar to the U, right? The U for union. So it kind of points the same way. Very soon we'll see another of these that will point downward. But this just means it's just another way to say inclusive or. And just read it like an or. All right. Then of course the next thing we can do is if we have our A and B. Another part or subset of this diagram we'll be interested in is this. This is known as the intersection. So let me just. This is the intersection between sets. And we write it as, so instead of the U, we do an upside down U, since in some sense it's the opposite operation. Right. So we write it like this. So in our case, right, if we go back all the way here, you can see it's everything that is in this shared middle set. So in this case, it's the numbers 2 and 4. Mm-hmm. But in more general terms, we can also express it as a set comprehension, and it's going to be very, very similar to the union. And why is it? Why is that? So A union B, right? We still want an X that's inside the universal set U, but in this case you can see, well, X could be in A, but it must also be in E. So what we get here turns out to be, instead of the OR we got before, we get an AND here. And luckily, there's not as much ambiguity compared to natural language. Everyday language, and means exactly the same, right? Like we want both things to be true. And once again, there is of course a symbol to express this and. It's perfectly fine to write the and, but of course this is math, so we have a way to express it. So I'm just repeating myself here. So we can, X should be in A. And we do that by doing the opposite arrow. What do you call it? I'm not even sure what it's called technically. Right. So this is a logical AND. Oops. Logical AND. Right. So these two are very important. Operations you can perform between sets, binary operations. So you take two sets and get a new set out of it. There's also a very important, this is a unary operation. You only take one set and get out a new set. This is called the complement. So in the previous examples we did for unions and intersections, the base set, the universal set, wasn't really important to us. But here when we're doing the complement, it will be, right? So we have the universal set here, and we have some A inside. And the idea is that whereas A is everything that is within A, here we'll have it to be everything that is not in A. So it'll be like this. And how we write this, if we say A, so either we write it by putting a bar on top of the A. In some books, you'll see it as adding a small c or big C. Adding a C as a superscript here. Yeah. But let's see what that would mean in our case. Let's go back to a base case. So we have A here. A contains 1, 2, 3, and 5. So those cannot be in the set. So that means that's 5, 6, and 7. They are the elements that is outside of A. Right. So that would be the thing in our case. Oops. It's 5, 6, and 7. And of course, since this is a unary operation, we could also ask ourselves what is outside of B, the complement of B. And we can see here it's what lies outside of B. So B contains 2, 4, and 6. So that means 1, 3, 5, and 7 are the elements that are outside of B. So it's all the odd numbers. That's a coincidence here, of course. Right. So these are examples of complements. So that's also a very important operation. And finally, I forgot a binary. There's another binary operation. What's it called? The difference or set difference. Let's call it the difference. Oops, that was wrong. How do I undo this here? Set difference. So here we have A and B. So for instance, the set difference A minus B, so we pronunciate it minus, but it's this backslash we use to denote it. Oops. So it's read A minus B. Well, what is that? Well, that is the elements that are inside A, but not inside B. So you can see it's was everything that's in A, but you kind of cut out the intersection. That's one way of saying it, right? So let's see, what would that be in our case? I keep referring back to it. So you can see here is this basically this moon shape to the left. So you can see it's the numbers 1 and 3, right? So because 2 and 4 are in B, they can't be part of this different set. In this case, it is A minus B. It is 1 and 3. We could also, you can see, take B minus A. You can see the idea is completely the same, but this time you get this set. So you can see that all the other, the intersection and the union, both of those are they're commutative, to use a fancy word, right? It doesn't matter if you say A union B or B union A, you get the same set. But you can see when you do a difference, so just like when you do differences of numbers, you'll find it's not commutative, right? So 5 minus 3 is 2. That's different from 3 minus 5, which is negative 2. And you can also see here what the difference is when it comes to this set difference. Oh, let's see what is in the actual set difference now. So you see, in this case, it's only the number 6 in our example here. Oops. Yep. How do we write this in set comprehension notation, in set builder notation? Well, let's see. So to go back to A minus B. So, well, it's something that's in the, well, it has to be in the universal set. But what we must have is that X is in A, and remember, and is this, and X is not a member of B. And here you can also see, using this notation, you can also see why A minus B and B minus A are different, right? That will mean you kind of move the doesn't belong to, you switch that between A and B. Okay. Oh yeah, that means that you can also, if you go back to the complement, revisit it. That means you can, if you have the set A, you take the complement of that, that is actually the same as the universal set minus A, right? Because you can see, if you take A, everything that is in U but not in A, that is exactly the complement out here. Okay, so this was a test stream. Before I end, there's of course one very important set. A very important set. I also forgot this when I went over it with my wife. There's a very important set. And this is of course what is known as the empty set. And so the empty set, it's like, if you do the brackets, well, it's going to be an empty bracket. There's nothing inside it. And because this is a little cumbersome, we have a special symbol for this. And this is like, you imagine a set and then there's a strike through to say, okay, there's actually nothing in this set. If you're from the Nordic countries, you may recognize this as an but you ain't got the AUO, so don't maybe don't think too much about it and just consider it a symbol, right? And it turns out, actually, what we've been doing so far is what is known as naive set theory. It's kind of like we're just finding our ways, trying to be rational about it. But if you wanna be extremely rigorous about it, you have to construct set theory through axioms and so on. This is pretty advanced topic. But it turns out the usual model of all math actually consists of only the empty set used in a variety of weird combination, right? Because you can, for instance, you could take the set of the empty set, or you could take the set of the empty set and the set of the empty set, and so on and so forth. So actually, in a certain sense, all of modern mathematics is just playing games with the empty set. Yeah, it's empty all the way down. Okay, I'll end the stream now, and yeah, I hope somebody will someday watch this. See you.